So last time we introduced Gauss's law, which is now written over here, right? So what it says is that the electric flux, which is defined by this integral, we call it phi sub v, the electric flux through some closed surface, closed is this circle here on this integral, and we'll call the surface S, is basically the electric field vector integrated over the entire volume. Okay, so it's E dot dA, and that's equal to the total amount of charge enclosed, Q enclosed over epsilon naught. Epsilon naught we defined as 1 over 4 pi times little k, which was Coulomb's constant. So, let's take some example here. We've got a bunch of charges, let's say, 3 positives, 2 negatives. We've just drawn some kind of arbitrary looking funny surface, S. So first of all, Gauss's law is always true. Okay, it doesn't matter if this surface is funny looking or if it's symmetric or if these charges are arranged in some weird pattern. It's always true regardless. S, again, must be a closed surface, so that means there's no holes punched through it, okay? So, if I cut a hole in the surface, there might be electric field lines that leak through that aren't accounted for if the surface isn't closed. So there's no holes punched in surface S. And Q enclosed is the net amount of charge inside. It's the positive charges minus the negative charges. That's irrespective of the arrangement. So, for instance, if I took this charge here and I moved it over there, as long as I kept them all inside surface S, it doesn't change the value of the electric flux. Okay? There's a couple things that we talked about near the end of the last video. So the first was that if we have no net charge inside a volume, right, so I'll take the surface S, then the net flux through it must be 0, okay? And if you go back to what we were saying about electric field lines, we said, okay, for electric field lines, the only place where they can begin, where they can start, the only source of field lines are positive charges. The only sink, the only place that an electric field line can end is a negative charge, all right? So let's, if there's no positive or negative charges inside here, then basically, every field line that enters that surface must also exit, right? Because if we said, there is some number of field lines coming in and there's some smaller number coming out, that means some of them must have ended inside. The only way they can end inside is if there was a negative charge, and we just said there are no charges inside. Okay, so that can't be the case. And conversely, if we counted some number of field lines going in and there were more coming out, the only way that could happen is if you had a positive charge inside, and we again said that wasn't the case. You can also think of this in terms of that fluid model that I was talking about last time. So in the fluid model, we said, okay, the fluid is incompressible. The only sources of fluid are the sprinklers, and the only sinks are basically these drains. If we don't have any sources or sinks inside, then all the water that passes into the surface must pass out. If that wasn't the case, then basically there must be some net amount of water either accumulating inside, right? And we said that since the water is incompressible, you can't stuff more water inside a volume. It just, the density is basically going to be fixed. We also said for a point charge plus Q that the flux, we solved for this actually, that if we took a spherical surface S, that the net electric flux out of it was plus Q divided by epsilon naught. And we basically just showed that by doing this integral, and that's just a restatement of Gauss's law. All right, so now I want to talk about a slightly more complicated example than just a single point charge. So let's take 2 point charges. Let's take a dipole. So I'll have a plus charge plus Q and a minus charge minus Q. All right? And if you remember what the electric field lines look like for this, they look something like this, right? So if I take a field line that is leaving plus Q over here, it'll just basically go directly to minus Q. One coming out here will kind of end it like that, right? They'll look something like this. Was a bad looking field line, but you get the idea. So that it'll look something like that, all right? So now let's draw some surface that encompasses both the positive and the minus charge. All right, so I'm going to start with one that looks something like like this. It's a closed surface. I'll call this surface S, right? So if we follow what we said from Gauss's law, we said, okay, the net flux, which is basically going to be sort of like the net number of field lines that exit the surface, should be equal to the net amount of charge enclosed. So here, because plus Q and minus Q are defined to be equal and opposite in a dipole, then there should be no net charge inside that surface S, right? And so what that means is that there should be no net field lines that exit. So we can see if that's actually the case, right? So, well, these field lines kind of, they never actually penetrate the surface, so we don't need to worry about them too much. We can look at this field line here. Well, this field line exits here, but it also punches back into the surface over here, right? This field line here exits here, but it re-enters here. So there's no net field line number of field lines coming out. Every field line that exits here comes back in. All right. So again, it's very useful to think of it, as quite different from this case of the single point charge, because here there is a net amount of field lines coming out, right? All these field lines come out, they don't come back in. In the case of a dipole, whatever comes out comes back in. And then, again, that's just saying in Gauss's law that there's no net charge inside because these cancel out, and so the net flux ultimately is zero. All right. And so in this example here, I was talking primarily about a very symmetric case, right? So I had a single point charge. I drew a little sphere around it. Can we see if that's actually the case for more complicated arrangement? So let's say, I'll take let me make one charge here. I'll call this plus Q. And then I'll put another charge here. And I'll make that 2Q, okay? Plus 2Q. So let's imagine now that we have some surface that's encompassing both of them. But it's not, a nice regular surface. It's some kind of weird looking surface that looks like this. All right. So what I can do then is I can think of, first of all, let me draw the field lines coming out. So I'll draw, let's say, 4 field lines for this charge here. And, well, let me back up, because, if I start drawing them here, they'll cross. Okay, so let me just start by saying, okay, what is the total amount of flux that's going to be coming out of here, right? So if we use Gauss's law, basically we say that I'll try to do a better job over here. So basically we said phi sub E should be equal to the total amount of charge enclosed, right? So it should be plus Q plus 2Q, so it should be 3Q, right? Over epsilon naught. Now, how can we see that, by, in terms of doing the integral, right? So that should be E dot dA. Over this, funny looking surface S. So one way to think about it is as follows, right? So we know what it is for a sphere. We did that over here. So you could imagine that the way we do this is we have one sphere that just encloses plus Q. This one we don't need to worry about because it's outside this surface. So we know that basically the contribution to the flux for we'll call this surface A, phi sub A should just be what we learned for the point charge, which is just, plus Q over epsilon naught. We could have another surface, again, a spherical surface that is centered at the plus 2Q. Call that B. And phi sub b would be, plus 2q over epsilon naught. And then we have this sort of surface that is everything else, right? So it'd be some kind of surface like this. Try not to shade it too much. So what you can do is think of this larger surface S as being comprised of, these green spheres that are centered on charge A and charge B, like we have over here. And then this sort of pink region, which is sort of everything else. There's a couple holes cut in, but it's still, you can think of as a closed surface because there's nothing that, at least when we add A and B to this, basically the whole thing will be closed. And there's no charges inside this volume, right? There's no charges inside the pink area. So by our argument then, E dot dA for some volume that has no charge inside should be 0, right? So we can kind of do this argument for basically the total flux through S, through surface S, as being 3q over epsilon naught by sort of doing the 2-point charges and then adding this other surface around it. So for the point charges, we do the spheres. We add this big surface around it that has no charge in it. And since if it has no charge in it, we can make it whatever shape we want, but the flux through it still will be 0. Okay, so then in the end, we just add the contribution to the 2-point charges. I hope that made sense. But, so it's kind of just a bit of a hand-wavy proof to show you that it doesn't really, we don't need to have, nice spheres around our charge distribution. We can really sort of make anything we want, and Gauss's law will always work. All right, so one thing to keep in mind is that Gauss's law is only talking about the flux, right? So the question is, how do we go from flux, which is an electric field integrated over an entire surface, to an electric field? Okay, so we want what we might want to know is the electric field. What we get from Gauss's law is the electric flux. So how do we go from one to the other? So I just wrote this out over here. So basically, what we get from Gauss's law is this integral, E dot dA. But it doesn't necessarily tell us what the value of the electric field is at some given point, right? I mean, what we would like to know, and this is sort of why we got into Gauss's law, is that it is basically a convenient tool that in many cases allows us to get the electric field at, all given points of interest. And the question is, but the law is only talking about this integral. So how do we go from this back to the thing we actually want, which is this, right? And so in general, it's not true that we can easily get the electric field from this in every case. So this, so Gauss's law is always true no matter what. But there's only a, few particular instances where we can actually get the electric field for that charge distribution. It turns out that actually, even though there's only actually a few specific instances, those instances are actually really, really useful, which is why we teach you Gauss's law. So let me just write that down here. So although Gauss's law is always true, it only helps us get the electric field, or helps us easily get the electric field without direct integration. In certain circumstances. Obtain E sub r. I should probably put some commas here. All right, so I don't know why I put that dot there. All right. So again, what it gives us is basically phi sub e, and by Gauss's law, that's basically Q enclosed over epsilon naught. In general, it's pretty easy to get the charge density, right? Or the total charge inside, right? So it might be integrating up some charge density. It might just be counting the total number of charges inside. So this is relatively easy to get in many cases. And so, this is basically equal to E dot dA. And like I said, what we want is actually this. We want E, right? So it turns out if we can basically write this integral as this, then we can actually get the electric field out relatively easily. Okay, so this is always true. Now, in certain cases, actually, it turns out that this integral actually can kind of be expressed as this. Okay, that's not generally true. It's only in certain circumstances, and the circumstances are as follows. So, first of all, we want we want basically a situation where this is true. We get that if the electric field is perpendicular or parallel everywhere on the surface. Two, the magnitude of the electric field. So you remember, this is a dot product here, right? So if it's a dot product and the electric field is sort of like changing its direction everywhere with respect to the normal vector on the surface, then that's kind of hard to evaluate. But if the electric field is exactly parallel or exactly perpendicular everywhere on the surface, if it's exactly perpendicular, E dot dA is just basically E times dA, because the vectors are basically parallel. If E is parallel to the surface, that means the normal vector is perpendicular. E dot dA is 0. Okay. If we also need the electric field, pretty much the magnitude, to be constant everywhere on the surface. At least it has to be constant everywhere that it's perpendicular. Where E is perpendicular to the surface. If E is parallel to the surface, then the dot product is 0 anyway, so you don't care what the magnitude of E is, because there is no field passing through any part of the surface where it's parallel. And 3, that the surface that we pick has to enclose some part of the charge distribution, right? That sounds kind of obvious. I mean, if we wanted to find, I don't know, the electric field from a plane, and our Gaussian surface that we picked basically had no charge inside it, then we would just say, oh, well, there's no charge inside, the total flux through it is 0, but that doesn't really tell us anything. So it has to enclose some of the charge distribution of interest. All right. So it turns out there's basically precisely 3 situations where we can basically use these, use these sort of conditions to easily get the electric field by using Gauss's law. And so I'm going to start a new page. So basically these are when you have perfect spherical symmetry, perfect cylindrical symmetry, and perfect planar symmetry. Okay? So basically 3 situations where you can easily get the electric field using Gauss's law. So 1, if your problem has spherical symmetry, or more precisely, if the electric field, or the expected electric field that you would get has perfect spherical symmetry. The second is if that electric field has cylindrical symmetry. I don't know why it keeps doing that. I feel like a 12-year-old girl. All right. And then the last is planar symmetry. All right, and we'll go through them in a little more depth in lecture and in co-op. But, so for instance, I just basically want to go through these rules that I wrote down earlier. So let's do the point charge, right? And we kind of went through it a little bit earlier, but, instead of a point charge, let's imagine just some ball, okay? But it's a perfectly spherical ball, and it has a perfectly uniform charge density, okay? So we have some kind of sphere of charge. It has some density rho. Could be a function of the radius out. It shouldn't be a function of the angles, because if it was a function of any of the angles, this thing wouldn't have perfect spherical symmetry, because depending on what direction you looked at the ball at, it may have a different density sort of closer to you, okay? So there's a sphere of charge, and it has some density rho. So in this problem then, right, so I'm going to pick, what I want to do is I want to have my Gaussian surface such that it basically fulfills these. So I have to decide on what surface I'm going to use. And the decision of what surface I'm going to use is that it basically fulfills these 3 conditions. Okay? The first is that the electric field is perpendicular or parallel everywhere on that surface. The second is that it's constant everywhere on that surface. And it has to enclose some of the charge distribution of interest, right? So, there's any number of surfaces I could draw for this that wouldn't work, okay? So I'm going to start by drawing some surfaces that wouldn't work. So my goal is, right, I want to know what the electric field is, right, at every given point in space. So basically my question is, what is E of R? And how can I use Gauss's law to help me? So I'll first start off with some sort of badly selected Gaussian surfaces. So I could make a Gaussian surface that looks like, I don't know, a box out here. All right. So it fails to satisfy this third criterion. It doesn't actually enclose any of the charge distribution of interest. And so how does this box actually help me get the electric field? at some given point. Well, it doesn't really. I mean, all I can say about this box is that it doesn't enclose any charge. So basically, the electric flux through it must be 0. But it doesn't actually help me know, what the electric field is at this point or that point. All I know is that the next net flux through here is 0. Okay, so that's sort of that's not a well-selected Gaussian surface. So this is, it's a valid surface, right? So this is a valid but unhelpful surface. Okay, I will draw another valid but unhelpful surface. So I will now enclose the charge distribution of interest, all right? But I'll make it look something like this. All right? And, we know probably the electric field because it's a sphere of charge, and the sphere is exactly, it's spherically symmetric in the sense that basically it doesn't depend on any direction that I look at it from. It looks identical from every direction. I can assume that the electric field will be radial, right? I don't know what the strength of the electric field will be as a function of distance, but I know, it should be coming out radially like this, roughly speaking, right? I haven't solved for the field, but, this is a good assumption that the field distribution should have this radial symmetry. All right, so let's look at this kind of now, amoeba-like surface and whether or not this helps us, figure out what the electric field is. Well, from Gauss's law, we know that, so if we said this thing has a total charge Q, then certainly it is true that the integral of and I'll call this maybe surface B, the integral of E dot dA over our entire surface B certainly will be Q over epsilon naught, right? But, if I look at the surface, there's parts where, so the normal vector is going to be kind of pointing in all sorts of funny directions because it's got this funny shape. So, over here, the normal vector, will be pointing like over this way. And so it's not quite parallel to this part of the electric field. So when I integrate that thing up, there'll be this cosine here. Again, the electric field, or the normal vector from the surface will be like pointing that way. So again, there'll be some angle with respect to the electric field. So, okay, I'm going to sum this thing up, but then, at all these different points, the electric field vector may not be exactly parallel to the surface. So then that's, some funny contribution in here. If I'm looking at the electric field out here, it's probably going to be, if the distance here is not the same as it is, let's say, here, right? So it's kind of bulged out over here. So this distance from the charge distribution is further than, let's say, this part of the surface. Then basically we know that the strength of the electric field is also going to be different out here. It's going to be a little bit weaker out here because the field is dropping, probably something like 1 over r squared, or roughly like that. But the further you go away, the field will probably be dropping. So if our field, that means that the strength of our electric field is going to be different on different parts of the surface. So this is kind of generally not a good surface to pick. Right, so going back here to our criteria, it did enclose the charge distribution of interest. That is true. But the electric field was not exactly perpendicular or parallel everywhere on the surface, right? The second thing is that the electric field the magnitude probably wasn't constant over the entire surface either, because, there's parts of the surface that were further away from the charge distribution and parts that were closer. So we really want something where the field is going to be, or the surface is going to be pretty much equidistant to the charge distribution everywhere on the surface. And second, that the field is going to be parallel to the normal vector of the surface. Or in other words, perpendicular to the actual surface itself. So there is one shape that works, right? And that shape, as I'm sure you've probably guessed, is a sphere. So basically, in the case of the sphere, the charge just, basically the surface is equidistant to the charge distribution at every point. So that means that the magnitude of the electric field should be constant over the entire surface. Also, since we know that the field lines are coming radially out, the field is exactly perpendicular to the surface at every point. It's punching out at 90 degrees. So we know that this E dot dA over here that will just give that dot product basically just gives us magnitude E times dA, right? So you can see here the spherical surface does satisfy this condition. The electric field is parallel everywhere on the surface. The electric field is constant because it's equidistant from the charge distribution, and it's enclosing the charge distribution. All right. So you can see here we can pick pretty much any Gaussian surface we want. This one here is just kind of irrelevant because it's not even not even enclosing this charge distribution. So, it's a valid surface, but it just is completely not helpful at all. This green one here, it does enclose the charge distribution, but then, it doesn't really help us get the electric field. If we wanted to use this green surface to get the electric field at this point, we couldn't really do it because, we know that all we know is that the total integral gives us Q over epsilon naught, but the electric field is sort of different at every point and it's pointing in different directions. So if we wanted to know the electric field at this point here, what we would have to do is just draw a bigger sphere, right? So for this bigger sphere now, we know that, so for the spherical surface, right, we have E dot dA, and we know that E, it's some function, maybe this thing isn't going to quite be like a point charge. I mean, it turns out it is, but, all we need to make the assumption is that the electric field is some function of R hat, dotted with the surface normal dA, R hat, right? That's basically what dA vector is. So you get an R hat dot R hat, so this is just then a scalar, right? So, and since f of R, because our surface here is basically, R is constant everywhere on the surface, right? So then we can basically just assume this is just some quantity. We don't need to worry about this in the integral. If in the green surface here, the distance, from the charge distribution is changing at all points because it's got this weird surface. So here we would have to keep this in the integral because, f might be bigger here, it might be smaller there. But for the sphere, we can assume that basically it's constant over the whole thing. So we can pull this f of R out. We got the R hat dot R hat, so that just goes away, it just turns into 1. And then basically we're left with the integral over the entire surface, dA, right? And so that's just basically then going to give us the surface area of that sphere. So it'll be, 4 pi R squared, right? And that gives us the Q enclosed. That might be a volume integral of this thing over epsilon naught. All right, so we're going to spend a little more time practicing this in lecture. So we'll try some other charge distributions and also in section.